This story is going to move more into the astrophysical today. Although hopefully we can appreciate some dual meaning in these systems, and we'll continue to bring up some of the mythology as it becomes relevant. To that end, let's review a little bit about what we talked about last time. I'm going to just call some folks here. Yeah, I'm really glad you brought that up. So she brings up the point that in becoming a more rational civilization, we, in some sense, and this was of course predicted by Nietzsche famously, the death of God and so forth, that we would move into this future age where each person would be stuck essentially with the task of becoming a super person, right? And have to define their own ethical frameworks and so forth, because this idea of an all-powerful deity was just completely untenable and repulsive to the rational mind, right? Which is interesting because, it seems like one of the more difficult parts of our society right now is that people are more individualized and atomized than ever before. Well, of course, Nietzsche knew this would be a nightmare too, actually. He thought that people would, the strongest among us would fare all right, but for the most part, people would suffer greatly because people really want to have a cohesive moral framework to orient their lives. And so, yeah, you bring up this point that, we got rid of, well, I don't want to speak in absolutes, right? I'm sure some of us still are part of religious communities and so forth. It persists, but it's certainly not the same guiding force that it was throughout most of civilization. So most of civilization, especially even recently, right, up through the Middle Ages, the church was the dominant force. The church was telling the kings what to do and so forth, right? Now today, of course, we have this interesting thing, institutional science, which is in some sense guided by the state still, which is quite interesting. There's a little bit of a role reversal there. However, the state uses institutional science to justify its actions oftentimes, right? Now, this is all done with the best intention, but I think what you're bringing up and what's really important is that, and this was really, really evident during this pandemic fiasco business where people adopted this slogan, like believe in the science or something like that, right? This is a real belief structure at some point. The idea is that there's really smart people who are studying things and that you should sort of, in some sense, even this phrase popped up a bunch, stop doing your own research. That was one of the most troubling pieces of the whole thing to me. And of course, it's all rooted in goodwill, right? There's this idea there's really smart people, they know what they're talking about. But this isn't that different than it was in the Middle Ages, right? There's these church people, they study the Latin Bible. You guys don't even speak Latin, so you can't possibly understand it. Listen to the church authorities, right? They know what they're talking about. They know what's good for you. And this was a really strong, cohesive force, right? In a very similar sense today, science is a really strong, cohesive force, especially the bigger, overarching, big science, capital S science, as if it's this one central monolithic narrative, right? But the truth is actually much more beautiful than that, although that can be troubling too. It's as we're starting to see, science, especially evident in astrophysics, is far from a single monolithic narrative. And we're going to, as we look at the birth of stars, and particularly the birth of planets, which are a lot easier to see, not sure if we'll finish that up today, but planets, there seems to be a number of ways that planets are formed, right? And there's competing theories about how that happens, and that's a really healthy ecosystem. And so in some sense, for the first few hundred years of the Enlightenment, in some sense, and I'm still sort of putting a model together for this, but it seems like the Enlightenment, so around the 1700s, when basically all of these scientific principles were born for the first time. The idea that you could do experiments and get to answers. The idea that the stars in the sky were material bodies that you could track and make sense of. There was this real spirit of openness to new ideas and open dialogue, open investigation. And that seems to be, in some sense, under threat continually in the last 100 years, which is very bizarre. So that spirit of openness really only lasted for a couple of centuries. And anyways, this is quite an interesting paradigm to be aware of. So whether or not humans can get rid of religion is still up for debate, or whether they even should is a different matter. And whether science itself is capable of providing an ethical framework is a whole other matter as well, particularly when it's funded by the state almost exclusively. That's a really interesting potential conflict of interest. Okay, cool. I'm glad we got to review that. It will keep coming up, of course. Let's see who else is here. It's the cosmology that has been popular for the last, not quite a century, but let's say 50, 70 years. Really became a hard science in the 1960s with the discovery of this background radiation. It very much echoes an older cosmology that's present in a lot of different cultures, right? This idea of this, well, it's called a world egg in some cultures. It's called this seed that hatches in other cultures. This idea that there's a point in time where the universe is born, and it's born in this almost divine event, right, which boggles the imagination and sort of defies mechanistic explanation. Turns out that's still the most popular scientific cosmology today. And so, you have to ask yourself, and many people are starting to challenge this narrative too, wondering if we haven't been completely led around by the nose by our pre-existing conventions about what should be. There's also this aspect of trying to see ourselves in everything. Humans are really strange animals. We really project ourselves onto everything around us. And so having a birth and a death ourselves, it's very difficult to conceive of anything not having a birth and a death. And I think that there's the danger of projecting that onto the universe itself. What was the other thing you mentioned before the cosmology? Oh, the hero's journey, yeah. The hero's journey is pretty interesting because you start seeing it everywhere. And it's hard to watch a movie these days without seeing this. The wheel, the circle of, and you can feel it in your own life too when you don't want to do something and then you kind of have to deal with it and you have to move through it. It's a really interesting archetypical experience. And so what I'm trying to present here is that when these things happen to all of us over and over again, our stories begin to reflect that because we're trying to, in some sense, understand what's happening in our lives. And that plays out in our cosmology as well. And that's the case that I'm going to try to make for you as we move forward. In some sense, if we don't have this nice birthday story for the universe, I think, troubles people because then it's not as self-similar to us as it seems, right? Why are we transient, but all of this remains or precedes us indefinitely? That's in some sense a bit alienating, perhaps, to our everyday experience. So that's interesting. All right, let's see if we can get one or two more people here. Yeah, the right-left brain thing is really interesting. So I remembered right after I left class that the lady whose TED Talk y'all should watch, who had the stroke, who was the researcher, her name was Jill Bolt Taylor. So write that down, check it out. It's like a 10-minute talk. It's really, really fascinating to listen to her story. Jill Bolt Taylor. Jill Bolt Taylor. You can just grab it on YouTube or something. Yeah, there's this really interesting, so there's neuroscientists, psychologists, they argue about this all the time. In some sense, there's this belief that humans have, there's a really interesting theory about this concerning the inception of language as well, that in the modern era, we are primarily a left brain dominant species. So the idea that the brain has two sides that are in some sense autonomous is really fascinating. So, a lot of animals actually are capable of turning off one half of their brain at a time to give it time to rest. So this is really important for animals like dolphins, right? Like, how does a dolphin sleep at night? It's underwater, but it has to breathe, right? Well, it turns out dolphins turn off half of their brain, and they sleep one side of their brain, and then they can use the other brain to go to the surface and get air, and then they can go back down, and then once that brain is rested, they'll turn on the other brain. Now, in humans, we don't have the ability to sleep one half of our brain at a time, but there is a sense amongst a number of philosophers that we have become really adapted to our left brain activity. So all the analysis, all of this academic, technological progress is the result of left brain activities, the ability to really order systems into their parts and so forth. And that makes a lot of sense. That in some sense is the defining human characteristic, the ability to we don't see what's really in a room necessarily. We see things as they function. Like, I don't know if you've ever thought about how bizarre it is that, there's two objects that look completely different. Like, the thing that you're sitting in right now looks absolutely nothing objectively like this, but they're both chairs, right? Because we see things for their function, not for what they actually are. And so that's the left brain organizational genius that's able to do that. But it comes at the expense of the right brain, and the right brain seems to be the one that's capable of finding new associations and seeing the peculiarities and differences and linking the different connections together. And so breaking that order apart a little bit. And in some sense, the hero's journey can be seen as this war within yourself between your left and right brain, where you have to make discoveries, and make new connections in order to defeat that monster at the end. This is the magical weapon that you have to find, right? It's the technology that arises. So yeah, I'm glad you brought that up too. And anyways, these concepts, we'll stop reviewing now, but these concepts continue to pop up over and over again, and I think it's really important that we stay aware of the human side, the humanities side of the approach to science as well. It can't remain just a left-brained process, because we'll get blindsided by our pre-existing orders that we've set up ahead of time if we're not cultivating that right brain side of things, That's part of the reason, so I guess it's worth mentioning. In addition to the final project in this class, you have the opportunity, if you want, to do an optional creativity project as well. And I think that's really healthy, and I'm going to try to meld those two together a little bit better for next year when we're reformatting this class. But it's really, really amazing to me every year what people submit. I mean, people take creativity projects way more seriously than analytic projects, it seems like. Yes? Oh, here's just like right on. Yes. And I think that's for good reason. It's a part of the brain that doesn't get exercised enough in the modern career ladder ascent, which is a bit tragic, because the truth of the matter is, if you really want to get to the top of some ladder in the world, which it seems most people do, you do have to have the ability to exercise that right brain, because you can't just keep doing what everybody else is doing. You have to move past that and move through it. And so I hope you guys will do that creativity project. It's worth actually a lot of points. You could probably essentially make up for not having showed up to class ever if you do that creativity project. But it's really cool, just the diversity. I really don't ask for much. I just want it to be pegged to something we've talked about somehow in some way. And so I've had people write short stories, poems, paintings. I actually ended up with a bunch of paintings on my walls from students last year that were really cool. Somebody made this painting of my cat in a spacesuit, like orbiting Neptune, I think, which was pretty crazy. I showed a picture of my cat last year. Anyways, so this is really healthy, and it's not just a trivial thing, right? Yes? Just questions about the creativity. Yeah, please. Project. Yes.
What are the parameters?
The only parameter is, well, the only guidepost is that you should peg it to something we've talked about.
So spacey.
Spacey, metaphysical, mythological, formation, any of this stuff, right? I mean, I don't think there's a more broad science class than the one that we're doing right now, right? We're talking about the formation of everything. It's right, everything material, everything mythological. It's a pretty wide-ranging topic. It would be hard for you to not fit whatever you're doing into it. That being said, I'll give people points based on how much effort they put into it. So if somebody sends me let's say, a poem that they wrote in one night, I probably won't give them as many extra credit points as somebody who's, put a lot of effort into a series of poems or written a short story that's been carefully crafted and so forth. Yeah, I mean, like I said, it's potentially worth as much points as having showed up to lecture. So it's like 10% almost of your grade. So you could bump your grade up a letter by doing this if you put your back into it. But it should be, it should represent that much work as well, I think. So that's something maybe you want to start toying with now in your minds a bit. And what I was going to say before that is that it's not just a trivial thing where I think that art is great because it's aesthetically pleasing and it makes our world more rich, which it does. That's great too. But I think it's really important to exercise those gears in your head and really get your right brain working, especially, it doesn't seem like most of you are science majors, and that's totally fine. Whatever discipline you go into, whether it's business or tech or finance, I don't know, whatever you guys are doing, the more you can exercise that right brain, the further it's going to get you in those fields. I really believe that. And it's something that's not necessarily as celebrated in the workplace as it should be, or in academia. I don't know, this school is pretty good about it, but some of the more technical institutions would be less inclined towards that. And there's actually this theory, I really think it's worth mentioning. There's this philosopher named Julian Jaynes who had this theory that, in some sense, he's trying to bridge the evolution of language and how this transition to the left brain world happened in humanity. And he has this pretty radical theory that for the first part of human history even, but definitely prehistory, humans were very much experiencing the speech in their heads, right? So, all right, so what does a thought feel like? Where does it come from? Well, nobody really knows, right? You have thoughts, you have ideas all the time, and it's like, well, where did that idea come from? And you might say, yeah, it's associations of things, and okay, fair enough. But James's idea was that people would experience these thoughts as voices, and they would literally think, they would hear their own voice in their head and think it was an external God talking to them, essentially. And then at some point, the left brain grabbed a hold of that voice, which was a right brain voice. It's kind of the background association voice, and said, no, that's me talking, and I am that voice, and these are my thoughts all of a sudden. And at that point, humans kind of evolved the ability to have a real ego, essentially, for the first time, which is interesting because if you have pets or dogs or cats, it's interesting to think about the way that they behave in a much more reactive fashion. Like they'll see something and do it. They're not really having this dialogue with themselves where they make plans as much. Now, it's not like an absolute story. There's certainly tendencies towards those things. But the idea that humans are in some sense very unique among the animals, along with a couple of other animals like dolphins and some whales, some elephants and so forth, they have the ability to really have this sense of self that's separate from the environment and that's separate in space from the environment, but also separate in time, right? You can project yourself onto the future and say, well, if I make this choice, what will become of me later? And that seems to be the defining human characteristic, is that we can make plans for who will become later as a result of the choices that we make. So this right-left brain thing is really fascinating. Okay. Now, where did we leave off? So we're going to move into talking about the birth of planets and so forth. It's really interesting because the first people who were really writing about the planets as being separate from stars were the Greeks. And the Greeks named the planets, and we basically have we have some Romanized versions of some of the planets, but they're from the Greek tradition. Now, the weird thing about the planets, of course, which if you have no astronomy knowledge whatsoever and you go outside and look at the sky and you look at it every night, you notice that most of the stars move in a predictable fashion as the Earth rotates. And you probably wouldn't realize the Earth is rotating, but you'd see the sky rotate over your head each night. And the stars would be in the same place. They have the same relation to each other. There's a few stars that move around in the sky. Some of them go backwards sometimes, right? those were what they called the planets, and that word translates roughly to wanderer, because these were the strange stars that seemed to move of their own accord. So the Greeks identified these with deities who had their own sort of motivations and will, which makes a lot of sense because they're doing what they want. And they identified, I think this is really, really much, much more profound than it's given credit for. Each one of those deities is associated with something which we all experience very generally and ubiquitously, right? We all experience Mars, which is like the god of rage, essentially. Or we all experience Venus, which is the god of love, or romantic love. Now, what's interesting about those experiences is that they seem to have their own programs that run out when you experience them, right? I mean, I know that everybody here has probably been super pissed off before, right? And it's interesting that when you get angry, it's actually, well, first of all, it feels kind of good because it's almost like your behavior is operating without you having to do anything, right? It's like you're kind of like surrendering your mind over to this emotion. We would call these emotions, I guess, in some sense today. But the Greeks thought of them as gods that would possess you, so you'd be possessed by the god of rage, right? And while you're possessed by this deity, it's sort of working through you. It's got its own will, and it's playing out like that. And the same goes for a lot of these names. Now, this is a really profound idea that I think summarizes in some sense how our brains are organized too. We have these programs that are built to help us survive, right? If you get into a situation where you need to defend yourself or your family against some threat, let's say it's a wild animal, well, you probably don't have time to think too much about how you should react to it, right? You're not going to sit there and make a plan and hash it out on the chalkboard with your family. You're just going to react to the threat that's happening. And so it makes sense that you would have these autonomous programs that would possess you and take over and hopefully provide, well, at least in so much as evolution seems to have played out, they have provided for our survival up to this point. But they can be a real nightmare too, because it seems like, in some sense, the job of being a human being, other than, providing for your survival in a material sense and having a career and all of this, your job is to integrate all of those different subsystems into a functional self, right? So that the birth of that I, the self, the ego, whatever you want to call it, the best version of that is the one that can actually take a hold of those autonomous programs and put them in order and actually make them part of the bigger self, so that when you feel, say the proverbial god of rage possessing you, that you don't have to essentially act upon it. You can feel it. Oh no, I'm starting to get pissed off. Is that something I really want to bring into the world right this moment? Is it going to help me? Am I fighting a wild animal, or am I just having a disagreement with my wife or whatever it is, right? So there's something really, really deep. And so the Greeks actually built their whole pantheon of gods with this idea that each one is subservient to the next, and that if you learn how to recognize these different spirits as they possess you, and you might say spirit is just synonymous with emotion or neuro routine. There's lots of ways to clinically wash this so that it's much more modern sounding. But the idea was established thousands of years ago, and it's actually quite deep and significant. So that was how the Greeks thought about the planets. Now, the Greek philosophers also began to understand that they were material bodies, and they were playing something out in the material realm, and that was worth understanding as well, which is really where our discussion turns today. So we have to start with the birth of stars, which is actually a much more difficult thing to understand than the birth of planets. Why is that? Well, I think we touched on it last time. Stars are born inside of clouds, and looking at something inside of a cloud is a real nightmare. But we do have some information, and so the story of the birth of stars is in some sense just like telling the story about anything in the lives of stars, is trying to assemble these snapshots that we have. And so the story that I'm going to tell you today is the best modern story we have for the birth of stars. But these processes take, tens of thousands, maybe millions of years to happen. And so we can't actually watch a star being born. And even if we could, they're buried in these clouds, so we can't watch them directly. So all we have are different second messengers for what is going on that point back to where they're happening. This will make a bit more sense, but I'm going to walk you through the story that we have today about how these stars come to be. And who knows, I could see it changing quite a bit in the future, but we'll see. Especially, a huge part of the planetary and star formation narrative is constrained, right? There's a limit on how fast or slow these things can happen, in particular how slow they can happen, because of our cosmology, which is quite interesting. So this story that we have, this birth of the universe story, has been constrained to about 14 billion years. Now, that's very, very, it seems like a long time, but actually when you think about the fact that life on this planet's been around for 3.5 billion years maybe, when you think that the planet itself, by the most conservative estimates, is only 4.5 billion years old, you run into a really strange feature. And the reason it's strange is because our star and the elements that are on our planet, well, let's start with our planet. Most of the stuff that's in this room could not have been made in our own sun, right? So there has to have been previous generations of solar systems that lived and died before our solar system was formed. So you can see that we start running up very quickly against a wall where it's like, how in the world is the universe only 14 billion years old, but the components of our own solar system came from multiple generations of stars when our solar system's only been around for 4.5, 5 billion years, right? There's a weird constraint on that limits our imagination, or at least the central narrative that I'm going to tell you today, in so much as how long it could have happened. So we're trying to hurry along a lot of these processes, or we have been historically, in terms of coming up with this narrative of where stars come from. All right, so we're looking at Orion here, and it turns out that this star formation process is pretty inefficient. Only about 1% of the material in that cloud right there has been turned into stars so far. Now, the leftover material eventually gets heated either by the radiation and wind from those stars that are forming, or from explosions of older stars that have died. And so these are, remember, we started off before with these really cold clouds and these little nucleations happening last time. But now there's other stars to consider who are living and dying, and they're injecting heat into the system by way of their own radiation and expansion and deaths, right? The deaths are really interesting, and we'll have a couple of talks about deaths, about star death coming on. All right. So the basic idea for triggering star formation is something like this. When a huge star is formed, so we're starting already with a big star being formed. So this is in a bit sense circular, but the idea is we need to have stars there in the first place, which is interesting, which in some sense I think points to a more circular cosmology than a one-way street like the one that we're moving towards in the main. When a massive star is already there, it's emitting a lot of ultraviolet radiation, and it also is ejecting this high-speed gas excuse me, in the form of stellar wind. And that injection heats up the gas around the stars, and it causes it to expand. So once those stars have used up all of their fuel, the hot gases start to pile into these cold molecular clouds and compress them. Now this is kind of, I think the best way to imagine this is storm formation here on Earth, which is really interesting. So, and I was actually out in the woods yesterday, and I was kind of feeling this a little bit. And this is this idea that when you get cold and hot gas, right? We have air, it's gas in our atmosphere. Same kind of thing happens. What do you have when storms form? You have a front, right? You have cold air, you have hot air. And they mix and swirl and form all sorts of dynamic turbulence and eddies. You get the nucleation of ice crystals, you get cloud formation. It's probably something really similar in the first moments of star formation as well, something very similar. And actually, the way that a hurricane is structured is quite interesting because the stars actually form these disks, which in some sense are dynamically equivalent to the way that hurricanes rotate, around this central point too, where you have a low pressure region, high pressure region, and you have this swirling effect that generates as a result. And the reason that you get this swirling effect is because it's simply the easiest way to dissipate all of that tension that's in that system between the hot and the cold air to even it out. So something like that is happening in the very first moments. Of course, you had the really cold gas that's been sitting around in space for eons and gotten stuck in the center of these clouds. These giant molecules have formed. It's very cold and still there. And now all of a sudden, that's coming into contact with fully formed stars that are heating them on the outskirts, right? All right. Now, so this idea that you would get nucleation and somehow organization of that turbulence, and nucleation, by the way, is a really interesting principle by itself. What I mean by nucleation is just the assemblage of smaller, say, molecules into bigger ones. This happens in cloud formation, happens in a lot of chemical processes. But at some point, this has resulted in enough local density, little dense spots, that gravity can start to become a player in the story. So let's see here. In this image here, you basically get a timeline for what we're looking at. When we see the very early stars being formed, you can't really see much because they're inside of this gas shell. But later on, the way we separate young from older groups, well, there's a number of ways, but one way is that after stars have aged for a while, they tend to sort of drift apart from one another. And that's by itself a sort of unexplained and interesting phenomenon, but it is part of the model here. And the reason it's strange to me is because you would think that stars that are big, in so much as a cloud can nucleate and gravitate together, its little nucleations, you would think that the stars would also be pulling towards one another, and you would get superstars as a result of the collision of all the stars, but that doesn't seem to happen. And there's maybe a number of reasons for that. The stars have this wind, right, that's pushing them away from one another. There might be something of that. They're enormously electromagnetically active systems too, right? So there's probably all sorts of repulsive activities amongst the stars. And so for whatever reason, as they age, they actually spread out a little bit. And so we estimate the age of these clusters based on that. All right. Now, this is another way of thinking about it. So there's a pretty big density difference between the molecular cloud core and the density of the youngest stars. You can't actually see this moment, and that's for a couple of reasons. One is that the dust is shrouding the interiors of these molecular clouds where the actual star birth is happening. And the second is that it's thought to happen really, really fast, actually, on the order of thousands of years. Now, I'm not sure. So at some point here, what's really interesting is that we have to surrender, because of the scope of this class, to the idea that people have constructed these mathematical models based on gravitation, based on mostly gravitation, actually, for how long these processes of collapse and nucleation take. And so when we're told that the initiation of this formation process takes a couple thousand years, we have to sort of take that on faith, which is a bit dangerous, but we don't have time to actually examine the assumptions themselves up front. What we can say is that people have now started considering chemistry for the first time, processes like condensation and nucleation, and how those might actually speed up the process so that you don't have to wait for a bunch of gas molecules to fall towards one another, which seems like it would take essentially forever. All right. Now, another interesting thing happens here is that just like in the storm, as you get these, yes?
I just had a question. I'm not sure if I'm understanding the diagram correctly.
I haven't totally finished the important part of it.
Yeah, just the gas pushes into it, creating a star. Is that what's happening in the arrows?
So
That's confusing me a
Yeah. Well, let me make it through the back half of this because this disk, I haven't gotten to this disk formation business yet. So there's one thing that we have to consider. I mentioned the hurricane not just because it's a good example of nucleation and condensation, but also because it spins, right? The arrows out here, I believe, are representing processes from existing stars, like their stellar wind, their ultraviolet radiation, right? Maybe even the explosions, supernova from other stars that are shock loading the system, right? Resulting in more density, resulting in more condensation, more nucleation. Now, what happens is that as material piles onto these central nuclei, these pre-star locations of increased density in the cloud, as it piles on, the star begins to rotate. And so I think the best way to think about this is the figure skater, right? Maybe you've experienced this if you've done any figure skating, probably not. Roller skating. What happens is when you watch, or you can just watch them in the Olympics or something. What happens is when they go and they start into these really tight spins, what they do is they start off spread out as much as possible. You can watch the skateboarder. Rodney Mullins is insane at this, actually. Anyways, they bring their arms in really tight, and it actually causes them to spin faster. And this is just a basic principle that can be derived from basic ideas of inertia that we were talking about before in gravity. But as material in your body even becomes closer to the central point, in order to conserve all of the momentum that's in the system, there's not as much of a reach of it, so you have to move faster, right? There's this interplay between the speed of rotation and the distance of that rotation. And in order to keep that quantity the same, the angular momentum, you increase speed as you bring your arms in. So this is something similar. This conservation of angular momentum is something that happens in these star systems very early, in these protostar, this moment of protostar formation. Those nuclei begin to swirl, much like a hurricane. They begin to spin like this. Now, there's something interesting that happens as that's going on. First is that if you're spinning and you're a ball, let's approximate you as a sphere, a baby star. The points of, assuming you're homogeneous, right? You're all one spinning at, together. All of your parts are spinning together. Actually, the parts on top of you, the poles of your rotational axis, they're actually spinning the slowest, which makes sense because the one out at your arm, like farthest away from you, has got to cover more distance in the same amount of time. Because of that, it seems that material kind of piles on to the top. Now, as the thing keeps spinning and so forth, at some point, the density increases. It's taking up more and more material. The density increases to the point that it's actually able to begin fusing material, and it generates its own wind. Well, what's interesting is that slower material kind of at your equator, it starts to kind of drag a little bit. And you end up getting to this point where you kind of flattened out almost like a disk because the slower moving material at your equator, the slower moving material at your pole is staying put. The things at your equator are trying to catch up. They're flying faster. They tend to spread out once again. So it's almost like the figure skater's arms are getting kind of pulled back out at some critical velocity. This is interesting because what it does is as your own wind starts to pick up, as you're actually starting to sublimate material, essentially solar wind is not so different than, this could be argued in different ways. But one way to think about it is something similar to evaporation, right? Where there's like a steam coming off of the surface. It's not an unreasonable way to think about it. It's much more complicated than that because you have magnetic acceleration of these gaseous molecules as well. But what my point is that now that you have this big disk around you of slower moving pieces of the same material of that cloud, the only place where that wind can really escape is out of your poles, right? And so one of the ways that we even have a sense of where these moments of star formation are happening is because we can see those jets of material, that's the wind, forming these big, long filaments. And what we do is we see those filaments because they're ionized and glowing, and we can trace them back to the cloud where we hope what we think is happening inside of that cloud. We can't actually see this moment right here, right? But we can see, and I'll show you some pictures here, we can actually see those jets that are streaming out And they look something like this. So we call these stars that are in this moment where they're just starting to emit their own wind and so forth. We call them T Tauri stars. Now, this is a good way to, I'll show you some more pictures of these. This is a good way to trace back where you think a star might be forming at and why we think these are some of the youngest stars, which allows them to be fed into our model of where they should be. So it's interesting because the protostar is still contracting at this point. It's not really a fully fledged star. It doesn't fit onto our nice HR diagram main sequence where we would expect. So we can't really place it on that diagram yet, which means we can't actually say exactly how luminous it is. We can't make these absolute observations without, these absolute proclamations without being able to observe something or fit it to the model that we have. Including, well, it looks like this, we think it's that old, therefore it belongs on the diagram here. And, you know, these are, by the way, almost all of these images are in the infrared, so that dust just still remains quite warm. And actually it turns out that when we start looking for planets being formed as well in the future, the best ones that we have a chance of seeing are the ones that are really young because they're still hot from all of that dust which has been cooked by the surrounding stars in these nurseries, in these nebula. All right. This is a special case of these jets where you actually have these two regions that point back to a central place. You have this separation we're hoping that the star is actually in the center of these two. These are called HH objects, which is named after their discoverer, called Herbig-Haro objects. And in this case, the high-speed jets escaping from the protostar are actually colliding with these lumps of gas that are also maybe would have become star-forming regions, but they're dense enough to become excited by the wind out of the poles of that newly forming star. So you get these kind of bookended objects in the sky. All right. Now, up to this point, we've only talked about individual stars forming, which is a bit perplexing because in reality, most stars seem to form in binary or triplet systems, which adds, you know, a sort of confounding level of complexity to this picture. But it does seem that each one of these these binary systems have their own disks that form around them, which is interesting, in so much as they're separated enough for us to even view them. It's possible that really close binaries have a single disk, but we can't actually see inside of the clouds to make that decision up. So what we do at this point is we try to summarize how this protostar changes by comparing it to the good old-fashioned HR diagram that we derived back at the beginning of the class. So as the star goes through each of its stages of life, its luminosity and temperature changes, and that kind of makes sense in so much as it contracts, it's going to get warmer, it's going to have, potentially it's going to become more luminous, although as its radius decreases, maybe there's less light coming off because you have less surface area, and so there's a balance there that we try to make sense of. So this is where the models and the calculations come into play. So a huge layer of assumptions here, which is somewhat beyond the scope of this course, is interceding at this point. So given a model for where a star is at any stage on its evolution, we then calculate where it's going to be later in its evolution. So at each step, the model, and by the way, model, I just mean mathematical model for the progression of how much stuff you can have in one place before it starts to move into a different stage of fusion or becomes fusing at all and so forth. So at each stage, the model predicts a particular luminosity and size for the star. And then from those values, we back calculate its surface temperature by putting it where it should be on this diagram. They call these actually evolutionary tracks because when it's first starting, it's actually, like I said, it's not able to actually exist directly on the HR diagram. So this is a good way of thinking about it. This red curve is the main curve on the HR diagram where we would expect main sequence stars to be, but they all sort of start off the main sequence so far. At least that's how we have it modeled at this point. So they're not quite, the young stellar objects, they're not even called stars yet. They're not producing energy through nuclear fusion yet. They're just deriving heat from gravitational collapse, just like the piston in your car, in your diesel car. And then at some point, these protostars are pretty cool. They have a fairly large radius, but it builds up as they collapse, right? And at some point, this gives us, as the collapse happens, we get these more like vertical trajectories that are leading down. It's going rather quickly. And then the star shrinks some more, gets smaller, and its total luminosity actually decreases a little bit. Remember, we have luminosity on the left of this graph and temperature down here. Now, the luminosity decreases just because the surface area is decreased at this point. That's the thinking anyways. But contraction slows down. It begins to actually retain its heat. And at some point, the stars become visible because we get that stellar wind appearing. And the stellar wind is, of course, accompanying fusion, which is happening inside of it as well. So this is when they're really starting to heat up and cook. So when the central temperature, let's say the stars reach something like 12 million Kelvin, which is a difficult number to comprehend, it begins to actually fuse hydrogen into helium, and we have got a star on the main sequence finally. Now, interestingly, some objects will never have enough material. They'll never accrete enough of this material to actually begin fusion. And this is becoming a really interesting piece of the puzzle, which is going to tie into when we talk about planet formation, because what is a star, what is a pre-star, they call them protostellar object, what does that look like if it can't actually reach the main sequence? Anybody have an idea? Take a shot. Yeah, they're dwarfy. So we would say it looks something like a brown dwarf. It might even, if it's smaller than that, look something like a Jupiter, right? Heck, maybe if it's really cold, it might look something like a Neptune or a Uranus, actually. And so this is actually one of, in my opinion, this idea that, if I was telling you the story of planet formation, which I'm about to move into, if I was telling it to you 10 years ago, I would basically be relying on our own solar system and trying to make a story up about how from this disk, right, we've talked about this disk in the star formation, from this disk, how all of the planets sort of condensed out of it and accreted. And I would tell the story of how that happened, and maybe I'd move the planets around a little bit while I was doing it. But today, especially with this new telescope this very expensive telescope they put in space over at L2 called the James Webb Telescope, been able to see a lot of very planet-looking systems that don't have a star attached to them, right? So it seems like there might be an alternate pathway for the formation of planets that doesn't even involve a star at all, right? Maybe a lot of these huge planets were on their way to becoming stars and never became stars in the first place. Now, there's an even more intriguing possibility to that, which I guess we'll get to. We'll unpack that one more in detail. But, when we talk about the death of stars, because the most popular way of talking about the death of stars is these violent, exciting supernovas, right? But is it possible that a star could just, lose enough material that it no longer has the mass to continue fusion? Could it just die really quietly? And what would a star that no longer fused look like? It wouldn't look too different than a star that didn't start fusing in the first place necessarily. Or maybe it would be different. Maybe it would have slightly different chemistry or so forth. But needless to say, it would probably look a lot like a planet. And so that's a really, really radical idea, which hasn't really been entertained too much until this very moment, that maybe these things can go both ways in some sense. So this story has expanded quite a bit in the last few years, and I find this really exciting because in some sense, it hinges a lot of these stories of where these planets come from, especially the ones that look a lot like stars, but not quite fusing. The time that it takes to make these things organize into something like a solar system, it stretches the current models of cosmology a little bit, right? Like I said, if the whole universe is supposed to have happened in merely twice the time, let's be generous and say 3 times the length of our own solar system, how do you get some objects that have gone through and almost became stars or used to be stars, how do they assemble into something like a solar system in such a short amount of time? Well, that is a difficult problem to solve, and I think that's why it hasn't really been answered in some sense, because of that restriction we have on the time length concerning the cosmology. So what you start to see, and the reason that I even bothering moving this discussion in general towards cosmology at the end of this course, is that cosmology holds the keys to the castle, right? Cosmology determines how much time we have to make these processes happen, and therefore determines what theories we're even willing to contemplate. Because if such a process is taking a bunch of preformed stars and sticking them together in a solar system takes, I don't know, 10 billion years, well, that's not enough time to have multiple generations of solar systems and to make the elements that we all know are here today. And so it's a theory that hasn't really gotten a lot of attention. But logic, and particularly these observations of these these planetary systems that have no star associated with them, have really given the astrophysical community pause to rethink some of these basic ideas. And so it's just a really, really, in one sense, a bit of a chaotic moment for astrophysics and planetary science, but it's also really exciting depending on how you look at it, because we're seeing things in a completely new light that we've never been able to see before. So a lot of these pre-stellar objects don't become stars, for sure. And what becomes of them? Well, they're very cold and they're very small, and so we don't know. And people try to estimate the number of these planets, huge ranges of estimates. They call them rogue planets, actually. And you can only see the ones that are really hot, and you can only see the hot ones with infrared because they're not fusing, they're not giving off visible light. So they're just warm, and we can see the infrared radiation, right? But the ones that are small and not super hot, it's almost like, who knows how many there are. There might be trillions of them just churning around in the foam in between star systems. We don't know. We're only going to be able to see the huge ones. Now, the James Webb recently, like I said, has seen some of these planetary systems. And the striking thing was not that they found rogue planets. The striking thing was that they found that the rogue planets were orbiting each other in little systems. That's pretty rad and pretty wild. So do you need a star to have a solar system? I mean, by definition, solar is in the word. But you could have planetary systems without a star. That's pretty mind-bending. This is where things get really, really interesting. So he asks, could they adopt a star later, or could a star adopt them? That's where I think things, I'm just completely, this is like completely outside of your textbook at this point, right? This is outside of anybody's textbook. This is where the real science is happening, though, and that's why it's so exciting. We don't know, but we know that when we run simulations so I met with this really cool astronomer who's at the University of Bordeaux in France, but he works with NASA quite a bit. And he basically has a computer game, for lack of a better word, where he can simulate all of these different things. Like how close and how fast would a star have to be moving by one of these planetary systems in order to actually capture it, right? And the crazy thing that he comes up with is he's like, yeah, it could happen. He's like, it could happen. It would be really rare. Like it would have to be moving at a commensurate speed, right? You'd have to have these planets orbiting. It would basically have to, maybe another star system would have to come by. Maybe it would lose planets in the angular momentum trade-off, right? Maybe as it grabbed a planet off of one star, it would change the orbits of the other solar system. But in some sense, this is what makes science. This is what makes this next revolution in science so difficult, is because we're talking about events that are not systematized, right? There's nothing predictable or systematic. Everything, this model that I've been painting for you of how stars form, it sounds really nice because it's this homogeneous story, right? It's like, well, there's this dust that collapses, does this thing, eventually the planets are going to condense out. Like, that's a really nice, simple story, right? But there's no chaos in it, right? And obviously the Greeks realized this, everybody realizes it. There's a lot of chaos in the world, right? There's things that happen that are completely unpredictable, and they're maddening in some sense because they drive the left brain nuts because they don't fit into that systemized, like, predictable structure for how we want the world. We really want the world to be this orderly, nice, predictable thing. We spend our whole lives ordering our lives so that they are predictable. But what happens? Well, you get sick, or you get in a car crash, or, like, God knows what can happen, right? There's a lot of chaos that injects itself in the universe, usually for the worse. But in some sense, it's also for the better because that's what leads to the birth of new entities and so forth. So I don't know how in the world the future of astrophysics will incorporate chaotic events because they're not predictable. And so because of the fact they're not predictable, they might occur very differently in different situations. And you're really looking for one in a million situations at some point. But whenever people, I've sat with other astrophysicists who are like, well, it's too rare. Like, that's just too rare. It would take too perfect of circumstances for a passing star to interact with another star and to just be at the right angle and the right speed to grab a planet. And my response to them usually at that point is something like, isn't it kind of weird and rare that we're a bunch of atoms that organized ourselves into people and are sitting here having a conversation? Like, that seems pretty rare to me, right? But it's here. It's happened. There's no denying that this is happening right now. Yes?
The dust and the rings. Have you ever experienced a grain silo explosion from the dust?
No, I've heard about those, though. What's the deal with that? It's static charge?
It's just so fine. The dust floats instead of settling, and they can't use cell phones or anything when they're cleaning those out because it's more explosive than dynamite.
That's really interesting. I don't know enough about that, but I'd like to learn more. Yeah, he mentions grain silo explosions. Anybody else heard of these before? Yeah, so dust, well, this is one thing that's really quite interesting. It brings up the electric side of this process, which we haven't touched on, which is another completely, I wouldn't say completely unexplored, but very much pushed to the sidelines in star formation is electrostatics. And chemistry is essentially a special breed of electrostatics. But in these dust silo explosions, I believe what it is that these little dust particles, they grind up against each other. And they build up a lot of charge as a result of it, right? Their atomic surfaces are getting, like, spooled up in this way that they have a lot of electric potential. And that electric potential can arc. And then there's combustion reactions that happen that I'm not totally aware of. But in some sense, the oxygen gets involved and you get an explosion. And it's really, really dangerous, right? There's been some complete cataclysms. So, and that's actually, the same thing happens in storms during lightning, right? Thunder and lightning. It's a very similar process where you have the buildup of charge and charge separation, and you eventually arc it, you ground it in this really violent explosion. There's some sort of combustion chemistry going on there too, which I'm not totally aware of. Thank God that lightning doesn't lead to combustion reactions in the atmosphere. That would be a nightmare. Just have massive explosions all the time. Maybe on some other planet it does. So yeah, electrostatics are playing out too. No doubt that all this dust swirling around is generating incredible, it must be generating things akin to lightning. And I don't know about combustion, because combustion, the reason I keep hesitating on the word combustion is it requires a particular reaction where oxygen is involved, right? And the production of essentially carbon dioxide and water is the result of oxygen interacting with different hydrocarbon chains. That's a really particular chemical reaction. But electrostatics and violent electrostatics and violent electromagnetism, again, just complete bleeding edge of where the theory is with these. So at several points in this talk, I keep saying the models calculate this or the models calculate that. The models don't take into account these kind of things at this point. They will in the future, but that's why I'm a little bit, I think we just need to take it with the grain of salt, that these models that we're using to estimate these charts and so forth, they're limited by they mostly were generated in the 80s, 90s, before we had any information with these really good telescopes about all these other formation processes that we have the luxury of analyzing today. So they're on the move. All this stuff is on the move. And there's more mysteries than there is certainty in a lot of these processes, which, you know, I'm personally really inspired by that. I think it's always exciting to me when and honestly, I doubt it, but if any of you go to become scientists, you know, these holes that you learn about are really where your future should lie, right? You know, you can definitely have a career in science where you study something that's pretty well known, like you refine one of these models that already exist or something. But when you start to see things that contradict, in some sense, this standard narrative, right? You kind of got to like open up your right brain a little bit and start thinking about, well, what the heck else could be going on that we're not considering in this model? What are the other features that we might be missing? That's what really propels these scientific revolutions into the future. That's the exciting stuff as far as I'm concerned. All right, so the next lecture, which I was hoping I should have started here today, but I didn't. We're going to be talking about planets, and we've already sort of started talking about planets. So the funny thing about, and we'll finish this next time, but the funny thing about this whole system, which, you know, I guess at this point it's probably not too shocking, but this entire idea of this nebula collapsing and the planets condensing or accreting out of it is a 300-year-old model. It's not that old, depending on how you count. It's about 3 or 4 people's worth of lifetime old, right? You know, if you just add up a few 100-year-old people, let's say, it's not that long, right? So it was established actually by these philosophers too, which I think is really fascinating. This guy named Emanuel Swedenborg, and that was in 1734, and then Immanuel Kant, who you might have studied in some of your more classics or humanities or philosophy classes. And they actually gave us essentially the model that we have today. Now, some expert astronomers might argue with me that we've tooled that, and indeed we have like added some, you know, more details to it, but the basic idea was put in place 300 years ago by these two guys. There's some serious problems though with that model too, and I think that the problems that I'm going to point out to you might be addressed by some of these new discoveries that are being made today concerning, you know, orbits in transition, the interaction between star systems, the changing of bodies between different star systems. And some of the biggest problems, there's 2 enormous problems with this model overall, which I think are worth pointing out. One is that this whole angular momentum business is one of the most foundational and easily observable processes in a physics laboratory. If you ever take a physics class, maybe in high school, you'll play with angular momentum. And conservation of angular momentum seems to be a law that you can't get around. Now, what's really strange is that the biggest body in a solar system is the sun, right? Just based on gravitational dynamics. The stars, they're the biggest ones by mass. Mass is, of course, calculated from orbits and so forth, right? What's really strange, though, is that the planets seem to have, at least in our solar system, the planets have something like 99% of the angular momentum. So if you have a really big mass, the really big mass, just like in the figure skater, should be the one rotating the fastest. That's another way, an easier way of putting it, perhaps. That isn't what we see, though, which is really, really just a head scratcher. And it's been a serious problem this entire 300 years since this model was erected. And people have come up with different ways of trying to save it. In other words, just to be absolutely clear, the motion, the rotational motion, so it's spin, but also its angular momentum in orbit for something like Jupiter has all of the angular momentum compared to the sun. The sun's barely turning, right? This is very, very strange, and it doesn't accord with the model I just told you of disk collapse and so forth. That's not the way that we would expect it to go according to this model of star formation that we just had. So what's going on with that? And I'll address some of the different consensus solutions to that, but I think that it's fair to say that it hasn't been a totally solved problem at this point. There's also this issue of, there's 2 more issues. One is it's really easy to take a bunch of boulders that are in orbit, like in the asteroid belt or something like that, and over millions of years to have them kind of gravitationally drift together. And then eventually you can imagine that those boulders start to assemble into mountains, mountain-sized objects, and then eventually you can get a planetesimal, and a bunch of planetesimals grouped together and you get a planet out of it. And this has been the traditional story. Fair enough, like that works. It seems like the physical calculations work out when you start with boulders. Problem is, when you start with a pebble, there's no way to get a pebble to turn into a boulder. There's no good astrophysical model for how, because what's up with pebbles? They're really light, right? And you have a bunch of pebbles flying around in outer space. Well, when the pebbles hit each other, bam, they just, a nice inelastic scattering, essentially, they bounce off each other. And this would happen forever. And so nobody really knows what to do with this I'm going to get in trouble if I say nobody. I'm sure somebody has some brilliant idea. Maybe they'll leave a comment on the video or something. But this is a huge problem. How do you cross that meter-sized gap where you go from little centimeter pebbles to meter-sized boulders? And nobody really knows. And it kind of goes along with this, just intuition that many people, and perhaps you or I have had, which is, how bizarre is it that the most dense object in the solar system is under our feet, actually, right now? It's kind of weird, because you would think that in the story I just told you about stellar formation, the densest thing was at the center of the system, right? So how in the world did the densest thing in our solar system end up out here, right? So these are kind of strange, bizarre puzzles that have troubled me, but also troubled, I think, the astrophysical community. And there's various solutions that are proposed, and they all leave me a bit wanting. And then there's some more radical proposals, of course, that involve something closer to these denser planets and stuff being the product of longer evolutions than we're comfortable with talking about generally in planetary science. So just to substantiate that a hair bit more, when we date the Earth, right, we say, oh, we've done radiometric dating of the Earth. It's an extraordinarily reliable method, and it is. The cool thing about radiometric dating is that it has its own checks and balances built into the method. So you don't just have one radioactive isotope that decays with a known rate of decay, and you can see how much of the daughter decay products there are relative to the mother, and you can make these nice curves that take you back to how old it is. That's nice, but you can do it with multiple different elements inside of the same sample. So you might have two different heavy elements that have different decay rates, and you basically get an X on the map where they cross, and so you can check the date of the rock. And so it's a fantastically reliable method. And people will say, well, we've dated the oldest rocks on the Earth to, let's say, 4 billion years old. So we know the Earth is 4 billion years old. Okay. The problem is not the dating method with this conclusion. The problem is that the only thing that radiometric dating can tell you is the last time that rock was melted. So the Earth seems to have been melted into a molten mess at, the farthest time that we can peg that to is maybe 4 billion years old. However, if you were in my class last semester, I believe I showed you this model for the moon's formation, which is a collision between the Earth and this planet Theia. Now, if you look at the NASA simulation of the collision between these two planets, both planets are completely liquefied during the explosion. It actually looks like two water drops hitting each other, right? So there's all sorts of situations where you can imagine that the surface of the Earth would be completely liquefied by impacts and so forth. And the fact of the matter is we don't have a direct way of saying how old this place is to begin with. It could be a lot older than we think it is, actually. Maybe it spent some time in somebody else's solar system. Now, we don't have any way of conclusively saying that was the case, but maybe. There's a really interesting piece of this puzzle. So I don't know if you guys are aware of this, but there's a period in Earth's history, unlike any other period in Earth's history, where suddenly the entire thing is covered in 5 kilometers of ice, tip to tail. The whole planet is covered. It's called Snowball Earth phase. Nobody knows why that happened. It's very, very bizarre. But, one interesting hypothesis is that if the Earth was in a different place, say the Earth wasn't even hooked up to our solar system for a few 100,000 years, would it be possible for the Earth to have frozen over, and would life have persisted potentially? This was actually after the inception of life, maybe less than 1 billion years after the inception of life. Well, it's interesting because you start to do the calculation, and I was going over this with Sean, the astronomer I was talking about with his sandbox universe. And what's really interesting is it wouldn't actually take that long for the Earth. Let's say that we just cut the cords that are holding the Earth to the sun right now, or another star passed by and pulled us off our chain. How long would it take us flying at the present angular velocity? So the Earth's orbiting pretty fast, actually. How long would it take for us to reach Proxima Centauri? Now, I'm not saying that Proxima Centauri would grab us up, but, stars are in different places at any given point in time. Maybe there were stars in different places back then. How long would it take, though? Just back the envelope calculation. And, you might think, it would probably take like millions and millions of years. Actually, it would only take about 40,000 years. So could some microbes have survived on the order of hundreds, maybe tens of thousands, hundreds of thousands of years under a nice insulated layer of ice? Probably, right? And it's going to be, it's going to be really shocking if we go to some of these moons that have these subsurface oceans we were talking about last semester. They're also coated in a big layer of thick ice, right? Well, if we find little critters down there, even little microbes and stuff, I think it will really reinforce the possibility of that hypothesis. Now, again, these are not ideas that the monolithic narrative of science is going to be super excited about entertaining anytime soon, because we really want that really orderly, nice story of things happen like this. They happen like this step happens, this step happens. It's really, really disturbing to think that, one day the Earth might just not be orbiting the sun for a few 100,000 years, right? That's not something that, you want to hear from your state, let's put it that way. And honestly, if I was a state bureaucrat, I would not be supporting that idea either, right? Because you want to give this image that you have everything under control. Like, the state is essentially, in some sense, an expression of our collective consciousness of wanting to impose order on the universe, right? That's the reason we have all these laws and the reason we have officials and police officers and everything is because we've all sort of collectively agreed that it would be nice if this place was in order at all times and the water was running and the electricity was functioning and the bad guys were locked up and so forth, right? And I think that our science, being a state enterprise at this point, is also in some sense really, really ambitious to keep that order locked down. And so, the story that I guess that I'm moving into, and maybe this would be a good place to pause, the story that we'll pick up with next time concerning the accretion of these planets out of the disks with some minor migrations, it is an extremely, extremely conservative story, right? It's also very much a story that's been around for 300 years, and the new data is really, really challenging this narrative. Not entirely, right? There may be room for this narrative to persist indefinitely. There may certainly be planets that do form in the way that we're going to talk about. But there may be other ways to form planets too, which are a bit more exciting. So let's put a pin in it, and we'll start with this central narrative of planet formation next time. And have a great weekend, guys, and stay warm. I will see you Tuesday.